In this episode, man versus snow.
How do we build a structure in this environment?
Be very careful.
There aren't any lifts like this in the world.
And the groundbreaking innovations from history.
It's incredible.
There's plenty of snow to collapse your typical roof structure.
That make the impossible possible. The Coast Mountain Range of British Columbia. 1,000 miles of vast chasms, towering walls, and ice-crowned peaks. Wendy Robinson lives and works in this extreme environment.
It's an incredible place to be. But we're on the coastal range, so we do have constantly changing conditions, extreme winds, extreme weather. You do get a lot of snowfall.
Mankind has been trying to conquer this type of environment since the beginning of time. But there's one place in particular where engineers are taking on all its challenges on an unprecedented scale. This is Whistler, British Columbia's most famous mountain.
Whistler has among the highest snow loads in the country. It takes a certain type of engineering and construction method to build in a town like this.
It's not just the snow, it's any time that you're working at the top of a mountain. You have to deal with wind, rain, lightning. We can get hail. It makes it very difficult to build in this environment.
Conquering Whistler requires mega muscle in the air, pure power on the ground, cutting-edge technology, and engineering that defies nature. Whistler is the biggest and busiest ski area in North America. It has a record-breaking cable car with an unsupported span stretching a staggering 2.7 miles. And it's home to the highest altitude suspension bridge in North America.
We're at the peak of Whistler Mountain at the very top, so the top of the Whistler Peak Express chair and above everything. It definitely takes a lot to build in an environment like this with the conditions that we deal with, but when it comes down to it, this is probably one of the best places on Earth.
When you're fighting nature on this scale, ordinary engineering just isn't enough.
It's a really formidable, hostile environment. Designing a structure in these conditions is incredibly difficult.
More than 23 feet of snow falls on these mountains every year. And when it gets out of control, it can be deadly.
You guys all set for me down there?
Me and my crew are just on our way, and we'll be about 10 minutes or so.
Yeah, you bet. We'll wait for you.
Copy that. Thanks, Ken.
Jeff Van Driel is one of British Columbia's Avalanche technicians.
So we're driving on Highway 99 here. This section is known locally as the Duffy Lake Road. I think a lot of people think of snow as being this soft, fluffy material, but avalanches have a significant amount of power and enough to destroy vehicles, to destroy trees, destroy buildings. They are a force of nature to be reckoned with for sure.
Avalanches have ripped through this region since time began, wreaking havoc and taking lives. And stopping them is impossible.
We are not going to be able to stop the avalanches. They are going to run one way or another. The worst case scenario would be that uncontrolled avalanches would hit the highway. Our job is to maintain the safety of the road and keep it open.
to control one of nature's wildest and most destructive phenomena. Jeff and his colleagues will have to draw inspiration from the early pioneering mountain engineers. Mechanical engineer Dan Dickrell is in Flagstaff, Arizona, exploring a solution that came out of left field.
All right, you ready? All right, here we go. That was a little high. So the game of baseball is a pretty old game, and the game itself is unchanged since the late 1890s, basically. What's interesting is the technology that surrounds baseball has evolved, though. So what we're doing right now is having a bit of batting practice. As the afternoon wears on, the accuracy of my pitches slowly deteriorates, but we use technology to enhance this practicing experience and take a little load off this old arm of mine. All right, here we go. Ooh, that was a good one.
In the 1950s, baseball practice was changed forever with the invention of the pneumatic pitching machine. Finally, human pitchers could take a rest.
This particular machine would be the grandchild of the original pneumatic pitching machine. I'm gonna take this baseball and I'm gonna drop it in. As I do, the compressor builds up air pressure in here. And once it hits a pressure that is sufficient to give me the exit speed that I want, all of that stored up air will be dumped into this barrel, forcing the baseball out and propelling it down towards the batters.
But one man saw another potential for this technology. For years, Monty Atwater had tried various methods of setting off controlled avalanches, including artillery and dynamite blasting. But after seeing a pneumatic baseball pitching machine in action, he had a stroke of genius.
Oh, check this out.
This is Monty Atwater's Avalancher, one of the last remaining examples of his literally groundbreaking idea.
If we look at it, we see this vessel here. This is where the compressed air goes. An air compressor gets hooked into this, pumping air in, pressurizing it, building up that charge.
Instead of firing baseballs, Monty's Avalancher packs a much bigger punch.
So I've got my explosive projectile. It's got some stabilizing fins, a remote detonator, and then I would drop it in, and then we would trigger it, projectile would shoot out. Ultimately, when it landed, it would detonate and hopefully trigger an avalanche. Now, the reason why this barrel is so long is because the longer the barrel, the higher the velocity of the projectile coming out. The higher the velocity, the further distance, the bigger the range that you'll have for this Avalancher.
This pneumatic-powered launcher was capable of firing explosive projectiles a whopping 1,200 feet into a mountain, starting avalanches from a safe distance.
This was a great solution to that problem of how do you trigger an avalanche without putting the people that work on the mountain in danger themselves.
All over the world, new generations of Avalaunchers are used to set off controlled avalanches from a distance, reducing the risk of a catastrophic disaster. But high up in the mountains that surround Whistler, avalanche teams will need engineering on a whole new level. Mountainous areas with heavy snowfall are prone to avalanches, capable of devastating the unsuspecting towns below in the blink of an eye. To reduce the risk of these often unpredictable falling masses of snow and ice, Modern-day avalanchers are used to set off controlled avalanches from a safe distance. But reaching the high mountains that surround Whistler calls for more innovative engineering.
Well, this is my office. It's a beautiful place to work, that's for sure.
Jeff Van Driel is in charge of a new detonation system that avalancher inventor Monty Atwater could have only dreamed of.
What do we got for temperatures up here?
I think we're looking at -2 right now.
An unexpected avalanche up here could be disastrous.
As we approach Blowdown Peak, path 51 here, you just see the road is just a sitting duck right underneath of it. And so our job here is to maintain an open highway by controlling the avalanches so that we can control when people are exposed to the avalanche problem.
At 7,500 feet, the 21st century solution has reached new heights.
And what we're looking at here is the solution to our avalanche problem. Yeah, Ken, so if you want to just bring us right up to the summit there.
In front of the shack there?
Yeah, that'd be perfect.
Okay, perfect. Yeah, I'll plan to make an approach. I think should be no problem setting us down on the peak here.
So these are our remote avalanche control system exploders. This is one of our key solutions to keeping the road open from avalanches. This here is the #1 exploder within our remote avalanche control system up here at the top of Blowdown Peak.
These huge spouts are the latest in avalanche management technology, known to Jeff and his team simply as exploders.
So what this does is sends a directional shockwave onto the slope. There's no actual projectile that will end up on the slope, littering the slope or anything like that. It's literally just a shockwave that stresses the snow and initiates the avalanche.
Huge metal tube-like structures called exploders are installed permanently into the mountain face. A shelter nearby houses canisters of oxygen and propane. Through a series of pipes, these exploders are fed a mixture of the two gases, which, once combined in the tube, are ignited by a spark. The resulting blast is expelled at great force out of the directional nozzle into the snowpack, and if the conditions are right, this will initiate the snowslide. Now, the team is able to set off explosions from much further away than an avalancher. By using radio communication, they can retreat to an extraordinary 15.5-mile distance.
Okay, connecting to the west rib. Fire in the hole.
When the risk is highest, the team temporarily closes the road and triggers an avalanche. They can then clear the debris and reopen the road quickly and safely.
Having this technology at our disposal definitely does save lives. It allows us to bring down the avalanches when we have closed the road rather than avalanches coming down and hitting the traveling public on the highway.
But runaway snow is not the only potential deadly hazard. What happens when all that snow melts? Mike Curry is part of a team at nearby Fitzsimmons Creek, responsible for protecting the town from the potential devastation flooding could cause.
We have these events that come down the creek that are akin to channelized landslides, or we call them debris floods or sometimes debris flows. If we had such an event, if we were to look up the creek, you'd probably see a frontal wave coming down with big boulders and trees, and it would be kind of coming like a bulldozer down the channel, like a small landslide. And in behind it would be a very turbulent, rocky flow with boulders and logs sticking out of it. It would be chaos.
A debris flood on this scale could rip through the town below. So Mike and his team have devised an epic engineering solution.
So this is the Fitzsimmons Creek debris barrier, the largest of its type in British Columbia. And the way the structure works is that the boulders and trees that can come down from the creek, they hit the steel pieces there, and the load gets transmitted into the two compression pieces on either side. So each one of those steel beams on the left there is a compression beam that is transmitting the load from the creek boulder impact into the abutment over there. And similarly on the other side here, we have a similar situation going directly to bedrock. It's designed that it will bend but not break during that kind of debris flow loading.
Protecting Whistler from a 1 in 2,500 year chance of a debris flood, the suspended steel barricade design is the only one of its type in the world. Perched above the creek, the 26-foot-high debris barrier is capable of restraining over 1 million cubic feet of debris. The town can rest easy, knowing that the Fitzsimmons Creek debris barrier will protect them if an extreme debris flood ever occurs. But engineers will now face their next challenge when it comes to building in the extreme elements.
Snow freezing and thawing and expanding as it freezes could literally split buildings in half.
Whistler in Canada. The biggest mountain resort in North America. It attracts 3 million visitors annually and is the site of a year-round battle between engineers and the natural environment.
You know, when we're flying up here, you get a really good perspective on the terrain. And this job really gives me a really good respect, a healthy respect for the forces of nature.
One of the biggest challenges engineers face is getting visitors from A to B. The Whistler region's most famous and popular peaks are Whistler Mountain itself and the neighboring Blackcomb Mountain. But getting from one peak to another could mean a long and time-consuming journey. So engineers have come up with an extraordinary solution. The peak-to-peak gondola. A world record-breaking piece of mountain engineering.
Be very careful and do not cross these lines.
Wayne Wiltsey has the job of looking after this mechanical giant.
So right now we're at the exit of the Whistler terminal and the cabins are heading off towards Blackcomb.
The peak-to-peak spans 2.8 miles, nearly 4 times the length of the Sydney Harbour Bridge. And at its highest point, it is 1,430 feet above the ground, almost enough space to fit the entire Empire State Building below. To achieve this groundbreaking piece of engineering, 4 giant towers were constructed on the sides of the valley. And on each peak is a station, strong enough to pull 28 gondolas, each containing 28 people, across a more than 2.5-mile gap.
That's the main drive bow wheel. These 2 wheels are guides, and why they have the 3 is to spread everything out so that we can get the large gauge that's required for the big cabin. Because of the size of the lift, we have emergency brakes or bow wheel brakes on all 3 wheels.
It took 2 years to construct the longest unsupported span aerial ropeway in the world.
So right now we're in the Whistler terminal, the peak to peak. It'll take us about 15 minutes to make the journey across to Blackcomb.
Most cable cars carry their cabins on a single moving cable. This haul rope is supported by a series of towers and loops around a drive wheel at each end of the journey. But take away the towers, and the cable is immediately put under extra stress. And in Whistler, the team is attempting to go further than ever before.
We're spanning the distance between two mountains. With one cable, with just a haul rope, it wouldn't be possible because the haul rope would not be able to support the load of the cabins.
The engineer's solution was a 3-cable system on an unprecedented scale. Cables, each weighing almost 100 tons, were produced in Europe and brought to the site using specialist heavy-lift transport. It took 11 weeks to stretch the cables across the valley. Each cabin runs on wheels along 2 static cables, pulled by a third moving cable that operates in an enormous 5.5-mile loop. The 2 highly tensioned static tramway cables provide strength and stability in the powerful mountain winds.
You know, think of them as tracks. Think of them as a railway, right? So those tracks support, and the cabins ride on the tracks, and the haul rope, which runs down the middle, pulls the cabins on the tracks from terminal to terminal. They were able to, with the track ropes, achieve the huge span.
This is unique mountain engineering on an epic scale.
When you go and you actually look through the floor or you look out the windows, it's kind of like flying in an airplane or in a helicopter. It's a pretty cool experience. There aren't any lifts like this in the world.
Building anywhere in Whistler means overcoming a host of extreme natural obstacles, even in the valley below.
Whistler has among the highest snow loads in the country, a country that sees a lot of snow to begin with.
Eric Karsh is part of the team behind building the Audain Art Museum, a huge new building that will need to cope with 23 feet of heavy snow each winter.
If you ignore the amount of snow that we have here, structurally, of course, it could collapse. From the point of view of snow masses freezing and thawing and expanding as it freezes, could literally split buildings in half if you don't account for it. So, yes, it's a somewhat dangerous environment.
With the threat of a fierce winter looming on the horizon, engineers will have to move quickly to create a building that can withstand the full force of Whistler's snowfall. In Whistler, construction of the massive Audain Art Museum is underway. But engineers will need to ensure that the building won't be buried under the 23 feet of snow that covers the region each year. Mount Hood, Oregon. A permanently snow-covered peak blighted by blizzards. Constructing a building to withstand this wild environment seems impossible. But structural engineer Nathan Ingrafia is searching through the whiteout for the answer.
So this area of Mount Hood, it's not unusual to get upwards of 20 feet of snow in a season, maybe 30. That's plenty of snow to easily collapse your typical roof structure.
Daring to build in these difficult conditions was prominent architect Gilbert Stanley Underwood. His mission was to build a hotel that could withstand the impact of devastating snowstorms.
And Matt, you could stop here. It's a good view.
What he came up with was the stunning Timberline Lodge. One of the most extraordinary and unmistakable hotels in the world.
This building has a really iconic shape. It's really, really a unique design.
Immortalized as the facade of the menacing Outlook Hotel in Stanley Kubrick's film The Shining, Timberline is instantly recognizable thanks to its unique roofline. Just like in Whistler, Underwood needed to create a large building with plenty of open space that could handle the heavy snowfall. The answer was a roof design called a cat slide.
So this model represents your typical steeply sloped roof. So you can see that this roof is very, very effective at shedding the snow. Now, if you wanted to make the building larger, to compensate for that, you would lower the pitch of the roof. So you can see with this shallower pitched roof that the roof collapsed under the weight of the snow that didn't easily shed off the roof. The way to solve this problem is the cat slide roof. To do this, we're gonna have to lose a little bit of the upper floor area. And now using a cat slide roof, the roof extends past this initial eave height all the way down to a second floor, if you will. Now using another identical bucket, you can see that that roof effectively shed all of the snow and no snow at all stayed on the roof. All of that snow that's shed off is now piled up just outside the building.
The ambitious 55,000 square foot Timberline Lodge finished construction in 1938. And its iconic cat slide roofs were the perfect solution to eliminating serious snow loads.
The concept, it's somewhat ingenious because it allows you to shed snow while also maintaining as much floor area as possible.
Just like the Timberline Lodge in Oregon, the Audain Art Museum's clever roof structure protects it against Whistler's crushing, destructive snow.
So we decided to have this really steep roof and a slippery metal roofing that allows the snow to slip and shed. And as you can see right now, there's no snow at all on the roof.
Like the hotel on Mount Hood, this roofline continues much further than in a traditional building.
That, from a volume design point of view, gives us a space in the middle of the volume that is quite high, where we can have a two-story space. And if you extend the roof beyond that two-story space, you end up with a one-story volume, which is the corridor that we're walking through right now, with a beautiful view to the forest. This way, you can maximize your floor area within that design. So we're in the mechanical well, which gives us a view of the roof from above. So if you look at the roof surface from the top to the bottom, you don't see any joints in the metal elements, which allows the snow to slip off unobstructed because the sheet metal is completely continuous from one end of the roof to the other.
The result is a cutting-edge art museum that can withstand 23 feet of annual snowfall.
To build in a town like Whistler, you can't be afraid of challenges. It's not the easiest place to build, but these challenges certainly made it an exciting project.
With buildings designed to withstand the snow, getting out and enjoying the powder is high on visitors' to-do lists. But taming some of the steepest slopes on the planet will require ingenious engineering.
So there's just not enough traction to hold up the machine.
In Whistler, British Columbia, engineers are facing a constant battle to keep Mother Nature under control. With the world's highest cable car up and running, the team is now setting their sights even higher. Their next goal, building a footbridge and viewing platform at the very tip of a mountain summit.
This pretty much scores at the top of the list for challenging sites.
Ryan Foster is part of the team that must conquer the mountain.
This location is one of a kind. It's almost like standing on top of a pyramid.
The Cloudraker Sky Bridge and Raven's Eye viewing platform will be 7,200 feet above sea level. The highest altitude suspension bridge in North America. This design requires tons of steel and concrete placed on the peak with pinpoint accuracy. But out in the wilderness, traditional construction methods are totally impossible. The solution is extreme air power.
So you can see he's coming in with the log.
The massive Kamoff KA-32 helicopter is designed to be a flying crane, capable of lifting extraordinary weights with ease.
He's got a bubble window, he's looking down. He's gonna bring it in and put it exactly where he wants it off the road. And he'll be placing it right now. And now he'll release the grapple, open up the claws, the arms, and fly away. Go for another turn. You need to be very precise.
Shane Palmer is in charge of a fleet of these monsters. They hold the key to building on Whistler's mountaintop.
So the helicopter's gonna be landing shortly. They're almost down to a fuel level where they have to refuel. I can feel the power right now.
The secret to its lifting power is in its twin set of rotors.
The intakes there of the engines are 2,200 horsepower right there. 44 altogether. The top set is going one way and the bottom set's going another way. So they have counter torque. That's why they don't need a tail rotor. And the way you yaw is they change the pitch on the top set differentially from the bottom set.
The two counter-rotating sets of rotors means the Kamoff doesn't need a tail rotor to stop the helicopter body from spinning. So every single horsepower is dedicated to lift.
Hang on. Get a thumbs up there. Everything's looking good.
The Kamoff can lift more than 5 tons at a time, making it the perfect machine for an impossible challenge, like building the highest altitude suspension bridge in North America.
So when we're erecting this steel, we're 100% working at height. There are 1,703 pieces of steel to connect. These are extremely heavy pieces of steel.
In Whistler, the Kamoff and other heavy lift helicopters allow engineers to build at more than 7,000 feet above sea level.
There's over 95,000 kilos of structural steel, reinforcing steel, and anchor bars. And so that requires a lot of foresight and a very careful plan.
The result is record-breaking mountain engineering. The 427-foot Cloudraker Sky Bridge and the Raven's Eye viewing platform.
It seemed like an impossible endeavor. Incredible piece of engineering that's gone into this. Walking out there, the bridge is a incredible experience to walk through with the metal grate so you can see through to the Whistler Bowl below. And then getting out onto that cantilever, I mean, you're sitting out 13.5 meters off the rock, off the cliff face, and looking down into snow and ice. It's an incredible experience.
Many of the challenges facing engineers in Whistler stem from having too much snow. But sometimes the problem actually is not having enough. Construction in Whistler is a serious challenge for engineers, thanks to the more than 20 feet of snow that buries the region each winter. But sometimes a lack of snow can be just as problematic.
You know, we have a pretty amazing area that we live in. Lots of steep slopes. Whistler's renowned for its steep slopes. And everybody, as they're skiing it through the day, they push the snow downhill, they push it to the side, and they build huge moguls.
The uneven movement of the snow can spell danger. Ramps can form and rocks can become exposed. The obvious solution is to use a snowcat to push the snow to where it is needed. But some of Whistler's slopes are so steep that an ordinary snowcat would end up sliding off the mountainside. On Vancouver Island, off Canada's west coast, mechanical engineer Agnes d'Entremont is searching amongst the remains of the once booming logging industry for one of the last surviving examples of an innovation that could help the team in Whistler.
This is a temperate rainforest that grows some of the largest trees in the world: Douglas fir, Sitka spruce, western red cedar. These trees were used for millennia by First Nations, but logging really got into gear when Europeans arrived, who built mills like this to process the logs into lumber. The challenge was getting those logs out of the forest, off the slopes, in order to bring them here to be processed.
Moving monster trees required a monster machine. This is a steam donkey. A mechanical beast with unprecedented power.
This is so rare.
Invented by logging entrepreneur John Dolbear in 1881, this steam-powered winch needed a skilled team to operate it.
Grab a chuck of wood there and chuck it in the fire.
Okay.
The puncher running the engine.
Yeah, there you go.
The spark chaser to put out fires.
Wow, you can feel how hot this is.
And the whistle punk, relaying signals to the choke setters who attach the logs.
Right. There we go.
Together, they could tackle jobs previously thought impossible.
Off we go, Joe. So right now, the logs are being lifted and dragged at the same time by the steam donkey.
But the steam donkey had another extraordinary skill. One that could hold the key to taming the snow slopes in Whistler.
It's incredible that a nearly 100-year-old machine can haul all of these logs. That's not all it can do. It can also haul itself, including to steeper and steeper slopes. And so to do that, they attach the cable around a distant tree and use the winch to haul this giant iron machine on these enormous wooden sleds up the slope.
Using the muscle of the winch allowed the steam donkey to go where no machine had gone before, transforming the logging industry and taming the forest slopes.
This is the office. and it never really gets old.
On the treacherous snow slopes of Whistler, it's modern winch power that holds the key.
Okay, away we go.
This is the Winch Cat. A snowcat with an added hydraulic winch on a 360-degree turret. It's the ultimate off-road vehicle.
If we didn't have the winch, we'd probably do it about 50 or 60 kilometers an hour about now. Like, we'd be going really fast. Conditions like this, there's just not enough traction to hold up the machine. The snow would just shear off and you'd slide.
A steel cable over half a mile long allows the vehicle to virtually dangle down extreme slopes and move snow exactly where the operator wants it.
What we have to do here, you can see that there's rock showing in the slope that has to be repaired. The boom is now over the cab, which is why it had that shape, so that we can see the rope in front of us as we're going uphill. So right now we're about 700 meters from where we hooked up the rope. You can see the rope in front of us way up in the air. And we are at 29.3 degrees. Pretty incredible, actually. The tracks are starting to slip now. This is a job that would be impossible with a regular snowcat.
Whistler might be one of the most challenging environments on the planet, but engineers refuse to let this world of snow and ice beat them.
It's a real privilege to be able to work with this type of technology. It's really spectacular, and I really enjoy my job.
By standing on the shoulders of history's innovators and adding their own imagination, determination, and daring, they are taking mountain engineering to unprecedented heights.
You know, if we didn't have this technology and this engineering in place today, we wouldn't all be up here enjoying the mountains. We'd be in the valley looking up going, wow, I wish I could be up there.
And making the impossible possible.